Hello everyone, I'm Himanshu Vasnani from Department of Mechanical Engineering, and today's subject is non-destructive evaluation and testing, subject code ME419, unit number 4 in the series, lecture number 31, and today's topic are infrared thermography testing techniques and infrared detector. So, learning objective for today is to provide the students with a basic understanding of infrared thermography testing techniques and infrared detector, and to know about the types of infrared thermography testing techniques. And the learning outcome after today's lecture is the students will have an understanding of infrared thermography testing techniques and infrared detector, and students will understand different types of infrared thermography testing techniques. So we have been studying about various non-destructive evaluation techniques in our previous lectures also, like visual inspection or liquid penetrating inspection and ultrasonic testing and radiographic testing, eddy current testing. So we have been discussing about them all the more. Magnetic particle inspection also we have studied. So infrared thermography is also a kind of a non-destructive evaluation and non-destructive evaluation testing technology, and it is useful in the industry because it is very helpful for preventive maintenance. Okay, so now we are studying about the infrared thermography testing techniques. Okay, so when it comes to infrared thermography, the testing techniques, so there are several options from which you can choose. Okay, your selection will depend on the considerations discussed, like including what set of data you are needing and what you are monitoring. So let's take a look at one of the most common infrared thermography testing techniques. Like if you, the first one is the passive thermography. Okay. Now this testing technique involves taking thermal images while the machine is running or immediately after operation. Okay. So this allows you to gather data without an external energy source or taking the machine offline. Well, this is really interesting because it is not asking you to give you an external energy source, because it will also consume some energy and it will include some cost. So it is better to have used this testing technique, because this kind of passive thermography kind of testing technique, this is involves taking thermal images while the machine is running, okay, or immediately after operation. Okay, so you will have a data which you can enter inside a computer for further processing. But this data that you have gathered, it will be without an external energy source. Okay, or you can, or taking the machine offline. So this is really good. And active thermography. See, this, as the name says, active thermography means that this technique, it requires an external energy source to create temperature variances in the component, which are influenced by interior materials and defects. Okay, now there are factors on which it is dependent, like interior materials and defects. Okay, so it is used to show how the heat flows through the component. Okay, how the heat flows through the component, and for locating abnormalities in components while in use. Now this is really good thing to understand, that this technique, if you compare the passive and active, see, the passive thermography doesn't need an external energy source. Okay, but here the active thermography, this technique requires an external energy source. Okay, and why this is required? To create temperature variances in the component. Okay, and this thermography, this is used to show heat flow through the component, and for this, it is helpful in locating abnormalities in components while in use. So this is really good. Okay, now we go with the flash thermography. Now this technique uses pulses of light to locate gaps or inclusions or other obstructions that block heat flow into a component. Okay, so this flash, as the name says, flash. So this means that this uses pulses of light, okay, to locate the gaps or inclusions. Inclusions means some external materials there in between the paint material, or some obstructions that block heat flow into a component. Okay, Now, vibrothermography, as the name says, vibrothermography means some kind of acoustic waves may be there. Okay, so they say that by introducing acoustic waves into a machine or a component, okay, so vibrothermography can determine where cracks may have been formed in the material. Okay, so this is a kind of a interesting thermography named as vibrothermography. Okay, so by introducing acoustic waves into a machine or a component, vibrothermography can determine where cracks may have been formed in the material. So the disturbances caused by the acoustic energy creates friction between the two rough edges. I repeat, the disturbances caused by the acoustic energy creates friction between the two rough edges on either side of the crack. So this produces heat which is deflected by the infrared camera. Okay, so there's a flash thermography, passive thermography, active thermography, vibrothermography. Okay, so vibrothermography is, it is a very you can say as the name says, vibrothermography. So very different kind of thermography technique. Then lock-in thermography. So like many of other techniques like lock-in thermography, it requires an external energy source, I kind of a light, sound, heat, etc. Be applied. Okay, the external energy source can be light, sound, heat, etc. Be applied to a component surface to reveal abnormalities below the surface. You are applying the source on the component surface and you are revealing abnormalities below the surface. So it's important to know the depth, size, and location of the abnormalities as well as the material makeup and properties for this technique to be accurate. So you need to have both the things available. First is the material makeup and the properties, okay, for for this technique, and then it is also important to know the depth, size, and location of the abnormalities. So while it takes longer than the techniques previously discussed, it can penetrate components with thicker walls. So this because it can penetrate the components with thicker walls. So obviously lock-in thermography will take longer time than the other thermography just discussed like passive thermography, active thermography, flash thermography, vibro thermography. So see each kind of thermography out of the five, because each has its own characteristics. Okay, like if you this would discuss about passive, that this doesn't require external energy source. Okay, and and it can, you can say, take thermal images while the machine is running, so it is good. Then active thermography, it as the name says, it requires an external energy source, and you can, so it can also helpful to show heat component, so this is also unique in its case. Then flash thermography, the name says flash, means it will use pulses of light to locate the gaps or the defects. Okay. Then vibrothermography. So as the name says vibrothermography, then you can, it is using acoustic waves into the machine and component. So through this it is determining the cracks in the material. Okay, and lock-in thermography. So it is using some external energy source to be applied on the surface and then revealing the abnormalities below the surface. So this lock-in thermography can penetrate components with thicker walls. So obviously it take more times than the other thermography. So every thermography technique is unique in its nature. It is having its own application. So depending upon the application, you can choose the type of thermography which you can technique of thermography which you want to use for its purposes. Okay. Now infrared thermography and preventive maintenance. Okay. Now let's go through it. Now infrared thermography is a highly recommended preventive maintenance tool in nearly all industries. You won't find another tool that gives you such accurate real-time data without disrupting the process flow from shutting down a system. Because we have discussed just now only in our previous slides also that on if the machine is working also at that time also with the help of passive thermography you can find out the thermal images. Okay, And you can also understand that the data which you are getting, the images which you are getting, that is the real time data. Okay. And you are not disrupting or stopping the process flow of machines. Okay, it is, the system is running, but you are just doing your own work. You are finding out the real time data and processing it accordingly in the computer as per the different directions of usage of this machinery. Okay, so this thermography, infrared thermography, you can say that it is a kind of a preventive maintenance tool. Okay. And when you talk about preventive maintenance tool, then they are very helpful in the industries. Okay. Because they can prevent some, you can say, sudden breakdown of machinery. And you know that if there is a breakdown in the machinery, then also it also involves time and cost, you know, and which can adversely affect the production. Okay. So, working infrared thermography into your regularly scheduled maintenance procedures is a great way to catch abnormalities in components and machines quickly. Okay, so if you include such kind of infrared thermography techniques in your scheduled maintenance also, okay, then we can also catch some kind of defects or discontinuities or abnormalities in the components. Okay, with the help of those thermal images. Okay, and processing those thermal images. So using baseline thermography on new component or after repairing equipment will provide a set of thermal images to compare all other tests against and lets you more easily troubleshoot future issues. See, I understand this kind of thing that they are just explaining you that uh, if you are going for a new equipment, then also you should go for such kind of thermal images, because what happens that if you are uh, checking the equipment after repairing, also after repairing the equipment, also you are just checking with the thermal images, then you can compare the all the data that was previously gathered on installation of new equipment and the data that you have gathered after repairing. Okay, which will help you to troubleshoot, or you can say more easily understand the issue easily. Why? Because when it was newly installed, it was working fine. So you have a database of saying that it will be working fine when when it will work like this. Okay, and when you compare it with other data, okay, so in that way you can have the understand the issues. You can have a comparison that where is the issue that is coming. So this infrared thermography is that much helpful. Okay, and the one important thing that it is providing you real time data. Okay, so that is really important thing. Now, let's discuss active thermography, a few points more in that. Then you can see in the diagram also on the bottom side, you have seen there is the excitation source, and then you have the influence of the defect on the on the thermal images. Okay, and then the thermal process excited by an external source. Okay, so you have something that is there with you. So, electrothermography is an imaging procedure for non-destructive material testing. Okay, you can see that there is excitation source in the diagram also, in the first diagram. Okay, it is showing that you have a excitation source, and then the second, you have a detector, an infrared camera. Okay, from which you are checking the thermal images. Okay, so they say that this active thermography is an imaging procedure for non-destructive material testing. Okay, so a heat flow is induced by an energetic excitation of the test object, which can be done in a transmissive or a reflective setup. So the resulting heat flow is influenced by interior material layers and defects. I repeat, the resulting heat flow is influenced by the interior material layers and defects. So if you feel that the heat flow that is going, okay, that is going, you can then it is influenced if there any defect is there. So these inhomogeneities can be captured on the object surface by high precision thermographic cameras. Okay, this inhomogeneity which can be captured on the object surface by high precision cameras. The additional application of different evaluation algorithms improves the signal to noise ratio. signal to noise ratio, which allows the detection of smallest defects. So we understand the precision of finding out the defects is so high with the usage of these thermographic cameras. Okay, they say that the when there's a heat flow, okay, this heat flow is influenced by the interior material layers, okay, and the defects, and if any inhomogeneity is there, then it can be captured on the object surface by high precision thermographic cameras. Okay, you can see that the influence of eradication on the component surface you can see in the second diagram. Okay, so let's go further. Now, active thermography uses an external source for measured object excitation. Okay, so that means introducing energy into the object. That we have discussed previously also that active thermography it works with the help of a external energy source. Okay, so the various excitation sources can be used for active thermography. Okay, and non-destructive testing. Okay, now, for example, laser heating and flash lamps, halogen lamps, electrical heating, ultrasonic excitation, eddy currents, microwaves, and others. So these are excitation sources that may have been used during active thermography process. Okay, and see, out of them, I think the flash lamps or the halogen lamps may have been used very commonly. Okay, the measured object can be heated by an external source directly, like by halogen lamps or hot air. That I just told you that the halogen lamps may have been used very commonly. So it has another application that it can be heated also by an external energy source. So the material inhomogeneities or defects cause then a distortion of temperature field. Okay, so whatever the heat you are giving, then the material defects they cause a distortion of the temperature field, and this distortion of temperature field is detected as temperature differences on the material surface. So another possibility is to use thermophysical processes. What? Another possibility is to use thermophysical processes in the material when mechanical or electrical energy is transformed into thermal energy due to defects and inhomogeneity. Okay, so it creates a local temperature source which cause temperature difference detected on the object surface by infrared techniques. So it is a case of ultrasound excitation, for example. Okay, so active thermography is very, you can say, commonly used, and you can see that the external sources which are used for active thermography are maybe like flash lamps or halogen lamps and ultrasonic excitation or microwaves, eddy currents, electrical heatings, laser heatings, and if you are heating the material with external source, then halogen lamps or hot air are the most commonly used, and this is helping the material to or the defects, okay, then they cause the distortion of the temperature field, which is this detected on the surface. In this way, this actual thermography works. Okay, then you can see some kind of thermographies that are discussed on the left hand side, and on the right hand side, you can see how they are done. Like there is a lock-in thermography that we just discussed, and it says that it gives you a periodic excitation, evaluates amplitude and phase shift, various excitation sources, possibility of large areas testing, longer inspection times. That we have discussed in lock-in thermography also, that it requires longer inspection times because it can penetrate thicker materials also. So it is helpful in that. So obviously, the excitation sources are there, and it is if it is taking longer inspection time, so obviously it can also help you to inspect large areas also. So if pulse thermography is there, then excited by very short pulse, okay, and analysis of the time temperature response, short inspection times, and only defects close to the surface can be. Because when you talk about pulse thermography, then also, as the name says, that normally the defects or the discontinuities that are there on the surface or close to the surface, that can be inspected very easily through this kind of thermography. Then the transient thermography. Okay, so you can see that the response that there's a pulse excitation and analysis of the time temperature response and detection of the defects, the depth, the short inspection time. So these are some features of this transient thermography. I'll tell you detail in the further slides also. But here they say that it also uses pulse excitation. Okay, and then it is analysis is done on the time temperature response. That is also done in the pulse thermography also, and the detection of the defects depth. While the pulse thermography was there, that it can detect defects close to the surface only, but transient thermography it is it giving detection of the defects depth also, and this also has short inspection times. Like transient thermography also has short inspection times. The pulse also has the same, the short detection times. And if you go for continuous excitation, the simplest case usable is special applications only. On the right hand side, you can see the diagram which is showing that you have excitation source and then you have infrared camera available with you. So you can see it is capturing the thermal images that is working on the surface. And you can see there the placement of the infrared camera and the excitation source on the two diagram, that is the diagram above and the below. It is has changed. Okay, you can see in the upper diagram, you can see that it is showing from the top side, top to bottom, it is going external source. But here, if you see on the bottom diagram, the source is on the left hand side, and it has been detected, and the infrared camera is on the top of the workpiece. So in this way, also it is taking the thermal images and helping finding out the defect or discontinuity inside the material. So you can see the placement of excitation source is also important, and the placement of infrared camera is also important. Okay, because our motive is to find the thermal images of the workpiece on the material and to detect the possibilities of defects inside it. Okay, so based upon the past experiences, you can do this. So obviously, the position of the excitation source and infrared camera is also important to find out the defect. Okay, so a lot of methods were developed for active thermography or for non-destructive testing measurement evaluation. And the evaluation method selection depends on the application. Okay. Used excitation source and the excitation type. It may be pulse, periodic and continuous. Okay. So in the simplest case, the response is evident from a thermogram directly. In the simplest case, the response is evident from a thermogram directly. However, it is necessary to use advanced analysis techniques in most cases. So the most common methods like available include lock-in thermography, pulse or transient evaluation techniques. Okay, and continuous excitation can also be used in some cases. I have shown you these techniques in the previous slide only. Okay, you can see that now again also that the lock-in thermography and then pulse thermography and then transient thermography, continual excitation. So I have discussed with you in short these kind of thermography techniques also. So they say that the response that is coming, it is evident on the thermogram directly. So we should understand with the common techniques of lock-in thermography or like pulse or transient evaluation techniques or continuous excitation is also there in some cases. So high speed cooled infrared camera with the highest sensitivity is commonly used for R&D application, infrared non-destructive testing application. However, research centers can test measurement configuration using uncooled volumetric infrared camera for survey application. So it can significantly reduce the acquisition cost of the measurement of the system. So we should know that also. That can significantly reduce acquisition cost for the measurement systems also. So you can see now the applications that are here, in the application you can see that what material is there, what a defect type is there. Measuring time is also important. cost, and more, they are important. Then these the applications, these are relative to these common things. Like if you click on the left hand side, you can see that the type of thermography you are using, like lock-in thermography or transient thermography or pulse thermography or concern. So the excitation and the evaluation method is also important. Okay, so these thing, all things are relative to each other. Like lock-in thermography will take more time because it can, you can say, it can penetrate inside the surface also. Transient and pulse thermography, these take short, these take short interval of time only for evaluation. Okay. Then if you take on the right hand side, you can see the excitation source that you are using. That what kind of source you are using? Either using a flashlight or a halogen lamp or ultrasound technique or electrical excitation, whatever you are using, the excitation source is all excitation source is also there. Okay, and the bottom side you have the infrared cameras. That what kind of cameras you are using? Either you are using industrial cameras or you are using high and fast cameras. So these all things are relative, and based upon that the application is there for all things. Okay, so the application, these depend upon the material, maybe on a defect type or measuring time. Okay, and the cost and more. So this diagram is basically explaining the relation between all of them. So the infrared non-destructive testing system available in the NTC center is modular. It means that the various excitation source can be combined with various infrared cameras and various evaluation methods depending on application that we just discussed in the previous diagram. Tested material, measuring time demands, size of the tested area, etc. Okay, so the modularity allows universal usage of the system for various industrial, scientific, and research applications. So there is a vast application for this thermography, infrared thermography. Okay, because it is also kind of a non-destructive testing system. So this is good for, you can say, for the industries. Okay, next. Now lock-in thermography. I will just discuss this in a faster way. That a modulated periodic source is used for the excitation, and the phase and the amplitude shift of the measured signal are evaluated, and the analysis can be done by various techniques. Okay, they're like halogen lamps, okay, and LED lamps, ultrasound excitation, or an electric current are suitable excitation sources. Okay, so you need to have a periodic source available for you, and the sources may be halogen lamp or LED lamps or ultrasound excitation or an electric current. Okay, they are suitable for excitation sources. It has the advantage that it can be used on large surfaces and it puts a low thermal energy on the part being inspected. Okay, so this is the main advantage of such lock-in thermography, that it is can be used on large surfaces. Okay, and it puts a low thermal energy on the part being inspected. So disadvantage is a longer measurement time and dependence of detection capabilities on a geometrical orientation of subject. I repeat, the disadvantage is that as a longer, it takes a longer measurement time. It is a longer measurement time and dependence of detection capabilities on a geometrical orientation of defects. Okay. Now the lock-in method is suitable for testing components with a low thermal diffusivity. Okay, if it is suitable, if you talk about suitability of this lock-in technique, a lock-in thermography technique, then you can say that it is suitable for testing components with a low thermal diffusivity, and it has many modifications for various specific applications like lock-in reference or lock-in online. This is a short about lock-in thermography. Okay, like pulse thermography is there also. So a very short pulse, usually in the units of milliseconds. Okay, we talk about that. A very short pulse, usually in the units of milliseconds, is used to excite the object. Okay, the cooling process is then analyzed. A flash lamp is typically used as an excitation source. Okay, this pulse thermography, you can see, understand that as the name says, pulse thermography. So it uses a short pulse, okay, in the units of millisecond, and it is used to excite the object. Okay, And after excitation, you can the cooling process is analyzed. Okay, a flash lamp usually used as an excitation source. So the advantage of this method is the speed of the analysis and a possibility to estimate the defects depth. Okay, since you can see that it is a pulse, so it will be the advantages like the speed of the analysis. The speed of analysis is very good, and the possibility to estimate the defects depth. So disadvantages of is a limited depth of the analysis, a limited area that can be inspected. Okay, with regard to a usable power of excitation source and a dependence of detection capabilities on geometrical orientation of defects. So it has advantage also, it has disadvantage also. The advantage is like that the speed of analysis is very good, and somehow you are able to estimate the defects depth also. But disadvantage is that is a limited depth analysis is there, and through thermography you can detect a very limited area. Okay, and obviously the dependence of detection capabilities on geometrical orientation of defects is there. So the pulse thermography has some good things and has some other things also. So we should be careful with that. Now transient thermography or thermal wave method. In principle, the excitation and the evaluation are similar to the pulse thermography. Okay, the excitation and the evaluation they are similar to the pulse thermography, but the pulse length is much bigger. Okay, the pulse length is much bigger in transient thermography as compared with the pulse thermography. So less powerful excitation source are required compared to the pulse thermography. This is the quite difference between the transient thermography and pulse thermography. That the the principle, the excitation and the evaluation style is same, but the pulse length in transient thermography is bigger. And for this, the less powerful excitation source is required if you compare with the pulse thermography. So in transient thermography, you require less powerful excitation source. So it is therefore possible to analyze larger areas and the measurement time is shorter than in the case of lock-in thermography. It is not comparing with pulse thermography, it is comparing with lock-in thermography. So if you compare with lock-in thermography, the measurement time is less in transient thermography, and also it is also possible to analyze large areas. Okay, so as in pulse thermography, the sensitivity of the method is limited by the geometrical orientation of defects. Okay, the sensitivity of this method is limited by the geometrical orientation of defects, and halogen lamps obviously are the suitable excitation source for this type of evaluation. That is common thing that we know. Now the applications, obviously the applications are very important. See, we have discussed about transient thermography, pulse thermography, and that lock-in thermography. Then active thermography we have discussed, passive thermography also we have discussed, flash thermography we have discussed. So these are vibrothermography we also discussed. So these are very you can say common techniques that is there available, but the purpose is the same to find out the defect or the discontinuities in the required material. So the applications are also very wide if you talk about this kind of technique that we are discussing, infrared thermography technique. Okay, so this you can say these distinct advantages have rendered thermography that is widely accepted by the industries in the quality and condition monitoring. Okay, then non-destructive testing for practical examples in the quality inspection is there. Okay, so condition monitoring for the rotating object, and then quality inspection in metal or non-metal materials, alloys or composites, pressure vessels and pipelines fault inspection is there, electronic devices investigation is there, then building evaluations such as wall, tile, bonding, integrity, concrete surface structure inspection, and CRFP concrete quality evaluation, and research work in material thermal properties. So it has own information. Now passive thermography, if you talk about it, then Passive thermography directly measures the surface temperatures for evaluation, since the interest region will have abnormal hotspots as compared to the surroundings. So, abnormal temperature profiles indicates a potential problem where the keyword is the temperature difference. Okay, what they say, that abnormal temperature profiles indicate a potential problem where the keyword is the temperature difference with respect to the surroundings. Okay, so the feature of interest are naturally at a high or low temperature than the background in this. Infrared detector, very common word that we are discussing nowadays. So infrared detector is a detector that reacts to the infrared radiation. So the two main types of detectors are like thermal and photonic photodetectors. Okay. Now the thermal defects of the incident infrared radiation can be followed through many temperature dependent phenomena. Like bolometers and microbolometers are based on the changes in resistance. Thermocouples and thermopiles are used the thermoelectric effect. Bole cells follow thermal expansion, and the infrared spectrometers and the pyroelectric detectors are the most widely used. So the response time and sensitivity of photonic detectors can be much higher. Okay, but usually these have to be cooled. These have to be cooled to cut thermal noise. So the materials in these are semiconductors with narrow band gaps. So incident infrared photons can cause electronic excitation. So in photoconductive detectors, okay, okay, this in photoconductive detectors, the resistivity of detector element is monitored. You know that the incident infrared photons they can cause electron excitation. So in photoconductor detectors, the resistivity of the detector element is monitored. So photovoltaic detectors contain a PN junction on which photoelectric current appears upon illumination. So in this way, this infrared detector works. Now the principle behind that, the thermal detectors contain a small active element on which radiation is focused. What they say, the thermal detectors, the principle say that thermal detectors will contain a small active element on which radiation is focused. So by blackening and insulating the element, and by minimum the size of the element, temperature change and reactor response is maximized. So temperature change is approximately inversely proportional to the exposed surface area of the element. So as the intensity of the radiation increases, the temperature diff change on the element or detector increases. Now some components of the infrared imager. You can see on the right hand side there are components like there are infrared waves, then you can see the lens is there, then there is a infrared detector, then your signal processor, and then the infrared image is there. So the detector, the first component we are discussing, there are two options for a thermal imaging detector, like cooled and uncooled. Both types of detector absorb infrared energy, which in turn affect the detector electrical properties to produce an image. Okay, so they say that there are two options for thermal imaging detector, either cooled or uncooled. Okay, and these both absorb infrared energy, which in turn affect the detector's electrical properties to produce an image. Okay, so these detectors they use narrow gap semiconductors to offer high sensitivity to infrared radiations. These semiconductors have to be housed in a vacuum sealed case and technologically cooled. Okay, so the next is the lens. So the lens is not made out of a glass like the lens of a normal CCTV camera. The properties of a glass mean that it does not transmit infrared radiation very well and would be an impractical lens material for thermal imaging. So instead, germanium is used, which is naturally occurring chemical element that is transparent to infrared radiations. Okay, that is, it will allow infrared radiations to pass through it. Now the sensor. They say that the ML8540 is a medium resolution, like an approximately 2000 pixels infrared image sensor that allows non-contact temperature measurement of an object and easy obtaining the thermal images. Like ML8540 receives infrared rays from an object at we can say 2256 pixels resolution and converts them into a voltage through a thermopile and selects pixels in accordance with the external CPU clocks to output signals. Okay. So in this way, this sensor works. Sensor process. So now the advantages of this infrared thermography are like that it requires no contact with components or machines. then there is a real-time output of this and can obtain data on large surface areas at one time. We have discussed this in like in transient thermography also we have discussed with that. Then there is the lock-in thermography. We have discussed this thing that you can obtain data on large surface areas at one time. Okay, and easy to read or visual images. And data can be uploaded to software for further analysis. And infrared camera offer great mobility and no downtime or production interruptions for testing. So the advantages are really good. And the disadvantages are also there that like infrared equipment is fairly expensive, obviously. So you should consider the cost of the time and the labor involved, as well as the saving you will receive with early detection warning from with infrared technology. So yeah, it has some advantages also, but it is expensive. Okay. So infrared technology can't detect temperature if a component is separated by a non-transparent material. Okay. Infrared technology can't detect temperature if a component is separated by a non-transparent material, which is glass cover. So when viewed with an infrared imager, the glass appears in a non-transparent. And infrared data requires significant expertise and an extensive knowledge base to evaluate imaging results. This is the points to be considered. Okay. Now the applications are very simple. And in medical and veterinary infrared applications is there. Then surveillance and security infrared applications are also there. Then mechanical equipment infrared applications are there. Electrical equipment infrared applications are there. So the applications are vast in like in medical field or security field or mechanical field or electrical field. So you have the applications in various you can say diverse directions. Okay. So other infrared applications are also there, like in process industry dry rolls, and you can detect condensate buildup and increased bearing temperatures. For storage tank, you can use this technology to determine liquid levels and inadequate insulations. Like for ovens and furnaces, you can detect insulation breakdowns. So you can see that the applications are increasing. And like for in a landfill, you can use technology to detect gas generation or leakages, otherwise invisible to that is human eye, and subsurface combustion or particulate fumes can be discovered. Water course pollution can also be detected, even building pest control. So the best thing is that you can use technology to detect gas generation or leaks, which is invisible to the human eye. So this is really good that you can use this technology to detect gas generation or leaks. Okay, this is important because it is invisible to the human eye. That is really good. Now, I think we should start with the MCQ now because MCQs are also important and really good to test that we have studied something good. Now, in passive thermography, okay, this technique, testing technique involves taking thermal images while the machine is running or immediately after operation. This allows you to gather data without an external energy source or taking the machine offline. It's true or false. So I think it's true in this case. Now, infrared thermography is the process of using thermal imager to detect radiation or heat coming from an object, converting into temperature and displaying an image of the temperature distribution. So it's true in this case. Okay. Now, electrothermography, this technique requires an external energy source to create temperature variances in the component, which are influenced by interior material and defects. So it is used to show how heat flow through a component and for locating abnormalities in components while in use. See, we have discussed about this thing in detail, obviously, because this active thermography I have shown you with the help of diagram also, and the plus point is that you can easily see how heat flows to the component. Okay, and you can locate the abnormalities or defects very easily in components. So it is true. Okay, you can find the defects very easily. So this active thermography is very helpful for finding out defects or abnormalities. So it is true. uh, the primary goal of infrared thermography is to confirm machinery is running normally and to detect abnormal heat patterns within a machine indicating inefficiency and defects. So it is true in this case. In flash thermography, this technique is use pulses of light to locate gaps, inclusions, or other obstructions that block heat. flow into a component. So it is true in this case. The answer is A, true. In vibrothermography, by introducing acoustic waves into a machine or component, vibrothermography can determine where cracks can be have formed in the material. And this disturbance caused by the acoustic energy creates friction between the two rough edges on either side of the crack. So this produces heat which is detected by the infrared camera. So see, this has a very good application, the vibrothermography. I think it's true in this case. Answer is A. Now, in lock-in thermography, like many of the other techniques, the lock-in thermography requires an external energy source like light, sound, or heat, etc., which can be applied to a component surface to reveal abnormalities below the surface. So this is true in this case. Answer is A. Now, in transient thermography, thermal wave method, the excitation and evolution are similar to the pulse thermography. However, the pulse length is much higher in transient thermography. So less powerful excitation source are required. Okay, if you compare with the pulse thermography, they say that in transient thermography, less powerful excitation sources are required compared to pulse thermography. So I think it's true in this case. Answer is A. Now, when true. Our infrared detector is the detector that reacts to infrared radiation. Okay, so two main types of detectors are thermal and photonic photodetectors. So I think we have discussed in our slides also. Okay, so the infrared detector is a detector that reacts with to infrared radiation. So two main type detectors are thermal and photonic, like photodetectors. So I think it's true in this case. Answer is A. Now the question can in thermography, the lens is not made of a glass like the lens of a normal CCTV camera. So germanium is used. Okay, germanium is used, which is actually a naturally occurring chemical element, which is transparent to infrared radiation. That is, it allows infrared radiation to pass through it. So it's true in this case. Okay, the answer is A. So we have discussed all about the MCQs till now, and the MCQs are also quite interesting. Okay, we have uh, discussed about the various techniques of thermography and found them that these techniques are relatively very easy and easy to understand, and it's very you can say interesting topic. So you can also study these topics from the references also and increase your knowledge in the current topics. So thank you all.